Lab 6, Faraday's Law. So here's a preview of the results. Experimentally, we calculated an average time for the magnet to fall through the aluminum tube to be 1.422 seconds, and then the computational model calculated 0.401 seconds. So the purpose of this lab was to demonstrate Faraday's law by observing the interaction between a falling magnet through a tube of aluminum foil. So the falling magnet causes changing magnetic flux in the aluminum tube, which causes an EMF and an induced current, and the induced current opposes the motion of the magnet falling. Then we modeled the interaction computationally, and then we compared our computational model to our experimentally determined time. So here are the physics principles. So Faraday's law, like I said, it states that changing a magnetic field produces an EMF whose magnitude is proportional to the change in magnetic flux over time. We also used formulas for electric flux, magnetic force on the wire, and then Newton's second law using the velocity and position updates. So here are the initial conditions, assumptions, and approximations. So the system was the bar magnet, the surroundings was the aluminum foil, and just everything around it, the earth. Initial conditions were that the magnet was initially at rest before being dropped, and we approximated the north and south pole of the magnet using a magnometer app on an iPhone. So for the experiment details, we, as I said, used the magnometer app to determine the north and south pole, and we took videos of us dropping the magnet through the tube. And we repeated this 5 times and measured the time taken for the magnet to go through the tube and averaged across the 5 times. And then we created a computational model to simulate this exact procedure as well. So here's the coding and computational model. So you can see on the left, lines 32 to 37, this is where we set up the geometry of the aluminum tube using measurements we found during lab. And then on the right, line 71 through 77, this is where we put in all the properties of the magnet. And then lines 97 through 101, this is where we're calculating the magnetic field of the magnet. Lines 114 through 121 is where we're calculating the change in flux. And then on the right, 148, this is the gravitational force in the magnet. 159, this is the current in the ring. And then lines 173 through 181, we calculated the magnetic force, and then we also added it to the gravitational force to get F net. So you can see here in line 185, that's calculation to get F net. And then in lines 189 through 191, we use Newton's second law to update the velocity and position. So here are the computational results. On the bottom left, we have a graph of velocity versus time, and then this is the computational model. All right, so interpreting the simulation, the red in the previous slide of the computational model corresponds to the clockwise current, while the blue corresponds to the counterclockwise current. And when you flip the magnet around, the dynamics of the system change such that the induced current is flipped, making it opposite in charge, but it's still equal in magnitude. We did find the experimental time was greater than the computational model, as said in the beginning, 1.422 seconds versus 0.401 seconds. This could be due to not accounting for air resistance or other potential sources of error. And the shape of the velocity versus time plot in the last slide tells us that the forces acting on the magnet were not net to 0 because the velocity changes over time. So what if the resistivity of the conductor were reduced as close to 0 as possible? So this would cause the magnet to move through the tube faster because greater resistance would dissipate energy from the currents induced by the magnet, and if there's less resistance, then there's less energy dissipation, and therefore currents opposing the motion of the magnet would be weaker, so it would go faster. And similarly, if there's holes or slots in the tube, this would reduce the strength of the induced currents, and there'd be less opposing forces on the magnet, so it would fall faster. So here we have potential sources of error, like I said before, not taking into account air resistance, and then human error, such as not dropping the magnet straight through the tube, incorrect calculations, and also the dipole moment of the magnet was calculated in lab 3, so that could be an error as well. Thank you.